All right, folks, section 9.2, summation notation, page 2. Let's get going. First thing I'm going to do here is I'm just going to rewrite the formula for arithmetic and geometric sequences at the top of the page. These are things I'm going to use throughout this side of the notes, and it's nice for you to know where I'm coming up with some of this stuff. So the nth term of an arithmetic sequence is equal to the first term plus quantity n minus 1 times common difference. And for a geometric sequence, the nth term is equal to the initial term times the common ratio raised to the n minus 1 power. All right, so enough of that. Let's take a look at example 2. It says rewrite the sum using summation notation. So take a look at this first one. What I see is plus 4, plus 4, plus 4, plus 4. So that tells me I have an arithmetic sequence with a first term of 6 plus n minus 1 times the common difference of 4. So let's write that in summation notation. I have to be aware that I have 5 terms and they are being added. So this is going to be the sum from n equals 1 to 5 of 6 plus the quantity n minus 1 times 4. You may choose to simplify that and write it like this: the sum from n equals 1 to 5 of, let's see, 2 plus 4n. That's what happens when you distribute the 4 and simplify. So either of those answers are acceptable. All right, let's take a look at example B here. Example B has something crazy going on. It looks like the sequence alternates back and forth from -1 to +1, -1 to +1. So it's not an arithmetic sequence because I'm not adding the same quantity each time. It's also not a geometric sequence, but it is a combination of the two. So the first thing I want to do here is I want to just look at it as an arithmetic sequence 10, 9, 8, 7, 6, 5. Okay, so let's just look at that. 10, 9, 8, 7, dot, 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 until we get down to 1. Okay, so that's an arithmetic sequence where the nth term equals 10, the initial term, plus n minus 1 times the common difference, which is -1. It's decreasing. So I can simplify that and say that it's a to the n equals, let's see, it's going to be 10, it's going to be 11 minus n. So if this were purely an arithmetic sequence that was starting at 10 and going down to 1, it would be 11 minus n. But it's not. It alternates back and forth between a negative number and a positive number. Now, if you recall in the previous page, we did see some sequences that did that, and we can achieve that with an arithmetic sequence. So to get an alternating sequence that starts with a negative number, we have to consider the following. That's going to be -1 -1 raised to the nth power. When n equals 1, that's -1. When n equals 2, it's +1. So that is going to give us our alternating negative and positive. Whenever n is odd, we have a negative number, a negative sign. Whenever n is even, we'll have a positive sign. So what does this look like in summation notation? Well, it's going to be this. We're going to sum from n equals 1 to 10 because there are 10 terms in this sequence. And then I have my multiplier that alternates the terms back and forth. And then I'm going to multiply by the arithmetic sequence of 11 minus n. So what happens if this first term is positive and then the second term is negative? All you have to do for that, folks, is put n minus 1 as this exponent. That'll force the first term to be positive and then the second term to be negative. Okay, we're going to jump down to part C here. Believe it or not, I know it's going to be hard for you to believe, but there's a typo in this problem. If you take a look at this thing, it's not arithmetic or geometric or anything. You could sit there all day and try to figure that one out. You're not going to. So that's a typo. Apologize for that. You deserve better. This really should be 1 plus 2 plus 4 plus 8 ... up to plus 128. At this point, let's talk about what these are. They certainly look like powers of 2 to me. It looks like I have 2 to the 0 plus 2 to the first plus 2 squared plus 2 cubed plus ... 128, if you're not aware, is 2 to the 7th power. So what I have is a geometric sequence where my first term is 1, my common ratio is 2, and my exponent will be n minus 1. Notice I didn't write the first term there of 1 as a multiplier out front because that's the identity multiplier. It's just going to give me back what I'm multiplying by. Okay, so we have our sequence definition. We do have to make sure we know how many terms there are. If we go from 0 to 7, we have 8 terms. So summation notation, I can write this bad boy as the sum from n equals 1 to 8 of 2 to the n minus 1. Some of you may like to think about this one differently. What if I make my n value match the exponents? I could go from n equals 0 to 7. That's still going to give me 8 terms. And then I would just have 2 to the n. So these two notations are equivalent. All right, let's move on to part D here. If you take a look at part D, you're going to wonder what the heck is this 1 doing right in the middle and how do I treat that? Well, if you look very carefully, my numerator, it increases by 2 here, it increases by 2 here. I wonder what number would be in the middle there. Well, that would be 5. And then let's look at the denominator. It increases by 1, then I skip something, and then from 6 to 7 is also 1, so that's also 5. So I can rewrite 1 as 5 divided by 5. And now it's pretty easy to see that our numerator, it increases by 2 every time. It's an arithmetic sequence that starts at 1 and goes up by a common difference of 2. I can rewrite that as 2n minus 1 when you distribute out the 2 and simplify. The denominator is also an arithmetic sequence. This one starts at 3, has a common difference of 1, so it's going to be plus the quantity n minus 1 times 1. This we can simplify to 2 plus n. And now we have both our numerator, we have our sequence defined. It's 2n minus 1 over 2 plus n. And there are 5 terms in this sequence, so I can write it as follows. Sum from n equals 1 to 5 of 2n minus 1 over 2 plus n. Okay, folks, that's it for example 2. Let's jump down to example number 3. Okay, so we're going to take a look now at 2 formulas here. Sum of arithmetic sequences and sum of geometric sequences. Basically here what we have is a formula that will do all of the work that we manually did over here on page 1. So all this stuff where we were having to add up all these terms manually, which could get pretty tedious the more terms you have, we now have some formulas to do that. The thing about these formulas, though, is they only work if you have a strict arithmetic sequence or geometric sequence. It doesn't work for any of the combo sequences that we've seen pop up from time and again. Let's first look at the sum of the arithmetic sequence here. So we're labeling this as capital S of the arithmetic sequence equals n times the quantity a1 plus a sub n, which is the first term plus the last term divided by 2, and then multiplied by the number of terms. So that should look kind of familiar. On the previous page, we had a couple sequences where we looked at the sum of the first and the last term, and then multiplied by the number of pairs. Well, n divided by 2 is the number of pairs of numbers that we have. So the same idea, just now put into a different format for you. So let's take a look here at 3a. I can see that this is an arithmetic sequence with a starting value of 5 and a common difference of 3. So I'm going to go ahead and figure out, if I want to know what the sum of the first 10 terms is, which is what the directions of this problem says, I need to know the first term, which that's going to be 5. I then need to know the 10th term, and the 10th term, when n is 10, I'm going to have 10 minus 1, which is 9, times 3, which is 27, plus 5, which gives me 32. So from those two numbers, I can then figure out what the sum of the first 10 terms is. Sum from n equals 1 to 10 of 5 plus quantity n minus 1 times 3. And actually, let me just shorthand that. Let me just call that the sum of the sequence a sub n. So we'll save some time and space there. That's going to equal 10, number of terms, times a sub 1, which is 5, plus a sub 10, which is 32, all divided by 2. And we're going to crank that out in our calculator, and we're going to get 185. So that's nice that we have that formula to make that problem go pretty quick, rather than actually adding up 10 terms. Moving over here to this next formula, sum of a geometric sequence is a little different. This one, if I want to add up the first n terms, I have to take the first term and then the term that goes one beyond. Notice this is, whoa, that's not what I meant to do. I need the highlighter. Notice here, if I'm adding up the first n terms, this is the first term minus one beyond, or n plus 1th term, all divided by 1 minus the common ratio. Let's see if we can apply that formula here to 3 part B. Clearly this is a geometric sequence. I have a starting value of 6, a common ratio of 1/2. Let's see what each of these terms that I need in the to sum up the first 10. First term is going to be 6. Then I need to come up with the 11th term, because if I want to add the first 10, I need to calculate the 11th. And that's actually going to be 3 divided by 512. And I'll let you prove that to yourself on your calculator. Again, this is a geometric sequence with a common ratio of 1/2. So we want to add the first 10 terms there. We're going to use this formula. We're going to say the first term, 6, minus the 1 past the last term, or the 11th term, 6 minus 3 over 512, all divided by 1 minus 1/2. And that's a we're not going to try and do that manually. We're just going to grip it and rip it in our calculator, and we're going to get a final answer of 3,069 divided by 256. There you have it. All right, I'm going to go quickly through these next two for you. So see if you can follow along. There you have it, folks. Two more examples. One with this arithmetic sequence here in part C, and one with this geometric sequence in part D. And hey, this one in part D, no, the numbers aren't pretty. They're not pretty at all, but that's the way some problems don't work out with nice numbers. That's just the way life is. All right, let's move on to part 4. And this actually, perhaps one of my favorite problems of the entire year, because what I'm going to show you here is pretty fun. You might want to sit around the holiday dinner table and amaze your family and friends with this one. I'm going to show you how to find an equivalent fraction for a repeating decimal. And I know right now that you probably find that that's a little bit too much to handle. You might want to sit down for this, because this is truly amazing. So I'm going to start by first of all, this is 0.12 repeating, and I hope you know that means it's 0.1212121212, and then that goes on forever. So the way I'm going to figure out what this is as a fraction, first of all, remember what the characteristic of a rational number is. A rational number, by definition, is an integer divided by an integer. And one thing we know about a decimal equivalent of a rational number is that its decimal either terminates, means it stops, or it repeats. So if this decimal is repeating, that means we can write it as a rational number. We're going to start by saying this. Let's just let x equal the original number, 0.12 repeating. And then what I'm going to do is I'm going to multiply x by a number so that I get one sequence of the repeat before the decimal. So that means I have to move the decimal 2 places to the right. That means I multiplied by 100. So 100x is going to be equal to 12.12 repeating. Now what I'm going to do is a little bit of algebraic magic. I'm going to say, let's look at our 100x here, and let's subtract x from it and see what happens. The equivalent equation to this would be 12.12 repeating, that's my 100x, minus x, which is 0.12 repeating. And 100x minus x is 99x. Let's see this. Okay, so the 0.12 repeating part cancels out, and then I just have 12 minus 0, so this is 12. That means x equals 12 divided by 99. I don't know about you folks, but I love that little algebra trick. Check it out on your calculator, do 12 divided by 99, and prove to yourself that that does equal 0.12 repeating. Now let's look at another example. Maybe, perhaps my favorite math, another of my favorite math problems. Is so exciting. For this one, remember what I said, we're going to start by letting x equal the original number, 0.9 repeating. And then I need to multiply this number by something so that I get one increment of the repeating decimal, one complete cycle of the repeat in front of the decimal point. So I only have to move the decimal one place to do that. So I'm going to multiply by 10. 10x is going to equal 9.9 repeating. Okay, then I'm going to set up the same equation I did before. I got 10x minus x, and the equivalent to that is 9.9 repeating minus 0.9 repeating. So we got two equations here, 10x minus x, that's 9x. 9.9 repeating minus 0.9 repeating is 9. Guess what, folks? When you divide both sides by 9, you get x equals 1, and this deserves a little bit of this. Whoa. That is unbelievable. 0.9 repeating actually equals 1. Some of you may not believe this, but trust me, it is true. Folks, we're done with this section. I hope you've enjoyed the video and WebAssign. Here we go.